You have a homework that's due Thursday. I've been told by people that they would prefer if I made it due next Tuesday. Is that true? Or do people care?
Next
Do you
Tuesday.
care? Okay. I'll send an email out saying that the homework's due next Tuesday. Let's see. Next Tuesday, you have the class is just going to be review. Okay. Today and Thursday we're going to go over two-way ANOVA, and then that's it for this class. Okay. Any questions? Yeah.
What day is the lab due?
What day is the lab? What did it? What is it? When is it due now?
Friday.
It's but you don't have lab session this Friday, right? What? So let's see. Yeah, different people grade the labs and the homework. So yeah, okay. So Tuesday, I'll send up an email that the lab is due Tuesday and the homework is due Tuesday. Okay.
Thank you.
Okay, so there's no lab. No, that lab that you have to turn in on Tuesday is your last lab. There's no lab on the two-way ANOVA, and I don't know. Any other questions? You guys know when your final is, right? Monday, right?
Will it be very challenging?
We should put up some practice finals very soon. We should probably have them up end of the week. And let's see. If you cannot take your final on Monday, get in touch with me because we have to do something before. Okay? Any questions? Yeah.
Will we be having a review session?
You will be having a review session next Tuesday. Okay? Any other questions? Nope? Okay. So let's see. Okay, so now we're going to talk about what are called multiple comparisons. So have you guys heard of multiple comparisons before? No? Okay. Well, how about this? Have any of you watched a sporting event before and heard people come up with statistics like it's never happened that 4 players have, hit 5 home runs or something in the game, right? You hear these random statistics and say this has never happened, okay? And how many times, and what do you make of those? Like, this is the first time that 5 people, all of whose last name starts with Z, have scored 2 points. Right? We've all heard this, right? And what do we think about it?
Cool story, bro.
They're exciting stories. They're like, hey, wow, that's kind of exciting, right? Or you might be like, I don't really care. But this is the idea of multiple comparison. If you test for enough things, even if they're random, one of them will do well. A very classic example of this is that if anyone ever looks at returns, right? You look at, okay, these are how I put money, I have a portfolio, I have money on these stocks, right? And then I'm thinking about, well, okay, let me look at all of the different types of allocations, right? Or, accounts that I could have, or all the different stockbrokers, right? And then you say, well, look, this stockbroker or this account has done better than everyone else in the last 3 years, okay? So what do you conclude? Do you conclude that that's a really good broker? Could be. It could also be, look, someone's got to do the best in all 3 years. right? There's some probability that someone is going to do well, right, over all of those 3 years, right? So again, this is the thing. If you check enough things, right, you're going to probably find something significant. So that's what we'll get back to. Okay? So let's think about this. So let's say you do a one-way ANOVA, okay? You rejected the null of no treatment difference. There's definitely treatment differences. And then you ask, what's the best? Right? So let's say we test 6 different medications, right? These are my treatments. And I find that, okay, well, if I look at them, the means of all of them are not the same, right? So there are differences in these treatments, okay? Now I want to ask you, what's the best treatment? Yeah? How would you go about doing that? Anyone? So, ignore what this says for a second, we'll come back to this, okay? But how would you do it? Just intuitively, right? We got 6 different treatments. We found out the means aren't all the same, right? So the effect, they don't have all the same effect. So how would you tell which one's the best? Yeah?
Can you do a hypothesis test for each pair of treatments?
So one thing you can do is you can look at each pair, right? I can say treatment 1 versus 2, 1 versus 3, 1 versus... So I can look at all possible pairs. How many pairs are there? Yeah, I have 6 choose 2, right? Right, so then I can check all of those, right? So that's one approach. One approach is pairwise all of them, right? What are other approaches? To tell which one's the best. Yeah?
Which one has the highest or lowest sample mean?
So you can just say, hey, let me look at the 6 of them. Look at the one that has the highest or the lowest sample mean, right? And saying this is the best, okay? So instead of comparing pairwise, we can just say which is the highest number. What's tricky about which is the highest number?
Maybe it also have the highest standard
It might also have the highest standard
deviation.
deviation. So then the question would be, well, okay, I can look at all of the z statistics, right? Right? Z statistic for treatment 1 up to 6. But how do I compare them? How do I compare one? Do I compare the first one against the second best? Right? Or how do I get a significance there, right? So, but that's one way. One way is you can, so we said all pairs is one way. But you can write this down. Right? One versus all in terms of you can look at the top one versus all others, right? What are other ways you can try to do it? Has anyone ever played tennis? Or looked at NCAA tournament basketball? What is one way of deciding what's the best team? Best team? You can run a tournament. You can run a single elimination tournament, right? You can take any 2, look at what's better, and then pass them on. So in other ways, you can do a tournament. And this is what we're saying, okay? We have a 5-way ANOVA. So 5 different types of treatments, so 5 different types of fertilizers. You want to know which one's the best. Naive strategy is to make one-sided 2-sample t-test for all possible pairs, right? Try 1 versus 2, 1 versus 3, 1 versus 4, 1 versus 5, then 2 versus 3, 2 versus 4, 2 versus 5, 3 versus 4, and 3 versus 5, and then 4 versus 5, right? And so there are 10 pairs. So these are 20 tests, okay? So what's the logic here? If each test is made at the 0.05 level, then even if all the fertilizer is equivalent, the probability of declaring one more than the other is what? So let's say we were only to do one test, right? Right? So 1 minus 0.95 would be what?
0.05
Which is called our
alpha.
alpha level, right? We're all good by this, okay? Well, what happens if we have 10, we do 20 different tests? Let's assume for a second they're all independent, right? So then what's the probability of getting a false decision, right? It's going to be 1 minus 0.95 to the 20. Why did we take 0.95 to the 20? Anyone? I know we did probability earlier this semester, but that doesn't mean you can forget it. Right? So why did we take 1 minus 0.95 to the 20? What are we computing? Yeah, it's 1 minus the probability of getting them all right, correct? And so that turns out to be 0.64. So what happens if we did 100 tests?
1 minus 0.95 to the 100.
It would be 1 minus 0.95 to the 100, right? So basically the logic or the problem is that as this number gets bigger, right, we're no longer getting 0.05, right? So this is telling that with 64% I'm going to make a false decision, right? And if I add more and more, the probability of making a false decision is what?
Close to 1.
Close to 1, right? If you do, so this is the point. If you do enough tests, unless you shrink your alpha value down with your test, with very high probability you're going to get nonsense. Okay? So one thing to suggest, well, we can come back to that, okay? If you make too many tests, the overall error rate increases really quickly. Okay, so how can we deal with this? So there are different ways of dealing with this, okay? So one way is something called the Fisher's least significant difference criterion. So what you do there is, once you know that you have one or more of the levels are different, then we look at all possible pairwise t-tests, and you use a critical value corresponding to the one-sided test at half the alpha level of the original ANOVA test. So, anyone want to parse this sentence? No? Okay, what you're trying to, so what Fisher's least significant difference is doing is it's doing the following. It's saying, hey, look, I found something significant when I did my one-sided ANOVA, right? So one of these treatments are different, okay? Now what I need to do is I want to test all pairs, right? But we can't test all pairs with 0.05 for each t-test. Why can't we use 0.05 for each t-test? Because it compounds and you get this problem, right? So what are we going to do for each t-test? What are we going to do with the alpha value for each t-test? We're going to drive it down, okay? We're going to drive it down in a way such that when I look at the combined test, right, my alpha value will be 0.05. Okay, so that's what this is saying. Okay. So one way to think about it, let's say we have treatments A, B, and C, and the means are 47.2, 51.8, and 46.2, right? This is their common variance. So then the LST will decide that two of the drawing methods are significantly different at the 0.05 level when x bar minus x2 bar divided by, these are my two samples, right? I pooled them, that's why I have these two. Is going to be equal to x bar 1 minus x bar 2 divided by 0.53 is greater than 2.306. Because this is a 0.025 critical value, right? So you can just divide it by 2, okay? And then you put that into a t-distribution with 8 degrees of freedom. If you plug that in, you do find that B is significantly better than A or C, but A or C are not significantly different. And these are a bunch of different other ways of doing this, right? You don't have to worry about the details of all of these. That's one way of doing it. So another idea, which is really important, is something called a two-way ANOVA. So what was the idea behind a one-way ANOVA? Do you guys remember? What were we trying to say? We were trying to say what? One of the treatments are different, right? Okay. So, and then when we talked about it, when we talked about the kind of this block design thing, right? We had treatment. One thing was a treatment. What was the other thing we looked at? Right. If we wanted to think about it as a matrix, right? What were the? What did we have in terms of? Well, we had treatments and what? We had treatments. What was the other thing we had? You guys remember? Blocks, right? So how could we think about that? We could have thought about treatments as what? What was an example of this that we made? Treatment could be
Spreading fertilizer.
Could be spreading fertilizer, right? So what would blocks then be?
Like a certain given area.
Like something about the area, right? It could be the type of soil in the area, right? Okay? So what we did not assume before was there was any interaction between the treatment and the block. So one way of thinking about it is, let's say we're treating people, there are 6 types of medication we can treat people with, okay? And we stratified the population into 6 types of, or maybe 3 types of blocks, okay? So you've stratified the population into people that are older, younger, and middle age, okay? Currently, the way we've modeled everything, there's no interaction between the treatment and one's age, okay? Now, it could well be true that there actually is a stratification between treatment and age. I think I told you guys this before, right? You guys, I might have. I told you about breast cancer, right? And the age of women, right? What did I tell you about that? Do you remember? I think I told you this, right? Or maybe did I not? You guys remember? Okay, so there's something that's interesting, which is if you look at certain states, there's they did a study between Rhode Island and Connecticut. And the reason why they chose Rhode Island and Connecticut is they're very similar demographically, okay? And they had one big difference. The screening procedure was really different. One of the states had a very aggressive screening procedure for breast cancer, and the other state didn't. I'm going to draw, do you guys mind if I draw the same graph here? Okay? We'll do dashed line is 1970, and let's see, I'm sorry, solid line is 1970, dashed line is 2010, okay? If you look at that, we haven't really done much here. This has gone down, and this has gone down, okay? So this second part, right, has gone down. So mortality for older women has gone down, and a lot of this is because of screening. The problem is these earlier cancers, right, often what you're due to some type of genetic defect, we have a very, very hard time treating, okay? So again, this is the idea of, well, this is just this idea that there could be an interaction effect between treatment and age, right? Your treatment would be what? Or screening, yeah, screening followed by chemotherapy or whatever, you know, or radiotherapy, right? So this is actually something that is really relevant in that there really are interaction effects between, right, things like age and treatment. So here are other examples. One kind of fertilizer works best on sunny fields, a different one for wet fields, right? One's better for lung cancer, a different one's better for stomach cancer, and you know, different people might want to learn in a different way. Okay? So how do we deal with this? So you saw how we wrote down ANOVA, right? When we went from treatments to looking at treatments and blocking, what did we do? We added an extra, it starts with an I. we added an extra index. So what do you think we're going to do? Well, let me first show you the equation. Okay, now we have 3 indices. Did we have 3 indices before? No. Okay, well let's start. Okay, so xijk. Okay, so let's just go back here, okay? I is the number of levels of factor A or B. I or J, right? So before we thought, and I'm really sorry before I called I L from now on, it's always going to be I, okay? It's always I, okay? I,
Was it L before?
just, it's always I. It's always, last time it was I as well, okay? And if I called it L, it's my bad. Just always call it I, okay? Just so we can always use capital letters for these, okay? So I is the number of levels of factor A. We can think of that as the number of levels of, let's say, treatment. And J we can think of as the number of levels of factor B. Block model. There's one difference. Let's go through this again. You guys remember what mu is? It is the overall mean what? Effect, right? Okay? What's alpha I? What's alpha I? You guys remember what alpha I is? Alpha I is the effect of what?
Factor A.
Factor A, right? And alpha J, before, what was this called?
Tau.
It was called tau, right? But we also called it alpha I at one point. And what did we call that? The effect of the treatment, remember? Okay? And what was beta J? That was the effect of the block previously, right? And now what are we calling it? We're calling the effect of factor B. Great. Did we have this gamma ij before?
No.
No. So what is this gamma ij? What have we added?
Interaction.
This is an interaction. It's saying, hey, what's the factor? What's the effect? If I'm in factor I, if I'm in ith level of factor A and the jth level of factor B, right? So previously we could have thought about it as the interaction between the treatment and the block. Okay? And then what's this? This is my noise. Okay? These are my errors. So again, these errors, we're going to assume that they're mean zero with an unknown standard deviation, and they're independent of the values for all the other errors. Okay? Okay. As written, this model is what's called non-identifiable. Have we talked ever in this class about what non-identifiable is or what identifiability is in a model? No? Okay. I guess we hadn't had to. Anyone want to take a guess what non-identifiability means in a model? Huh? You won't be able to fit the model. It's actually very simple. Yeah.
Does that have to do with like number of unknowns and number of equations?
It does have to do with the number of unknowns and the number of an equation. What non-identifiability means is that I can stick in 2 different sets of parameters, let's call it theta 1 and theta 2, and I get the same likelihood. Okay? Do you see why that could be a problem? If the same parameters, right? If different parameters give you the same likelihood, that's a problem. So you can fix this. The way you fix it is by adding these constraints. Okay? And what are these constraints telling me? Alpha 1 through alpha I are equal to 0. Beta 1 through beta j is equal to 0. And the sum of all of the gammas are equal to 0. Okay? What does it mean that all the alphas added together are 0? Anyway, no reason. Why do you think I added these constraints? I want all the alphas to be 0 for the following reason, right? let's say I took all of my alphas, right, and I added tau to them. Okay? That would, if I ignored these things, that would be the same as adding a tau to mu, right? So I want really mu to cover the baseline, right? If I say, look, don't worry about the levels of either of the factors, right, or any of the interactions, that should be covered by mu, right? None of that should be falling into these, okay? That's why we want this to be 0, okay? Similarly, that's also why we want these to be 0. And that's also why we want these to be 0, okay? Because we don't want any shift in any of these. We want all of that to be absorbed into the mu, okay? So that's why we add those. Okay. So now we have 3 hypothesis tests. What did we have before in the randomized block design? We had 2, right? What were the 2 things we were testing for in the randomized block design?
Whether the blocks were different.
I'm sorry?
Whether the treatments were different and the blocks were different.
Yeah, whether the treatments are different or the blocks are different. So now what do we added in terms of a 3rd test? Whether the interactions are different, right? So now, this is one of our tests. Are all levels of factor A equal? Versus at least one of the levels of factor A is non-zero. Similarly for factor B. And then, here we go. The interaction terms are all 0. Or the null hypothesis. I'm sorry. Yeah. Right. Yeah, the interaction effects are all 0. And the alternative, at least one of the interactions is non-zero. Okay. So let's say we find that the interaction term is statistically significant. Then we immediately decide that both of the main effects are also significant no matter what the result of the test. So let's talk about this. Let's say we were looking at this, right, and we found that the interaction term is significant, okay? Let's say if that were true. Then I would ask you, does that mean both factor A and factor B are significant? Is it possible that the interaction will be significant, but factor A and factor B by themselves are not? Yeah.
What does it mean by the interaction is significant?
What we mean by the interaction being significant, coming back here, is that all of these, one, right? This is not equal. One of these are not 0. At least, right? If I come back to the model, if one of my gamma ij's are not 0, right? What does that mean? If one of my gamma ij's are far from 0, if I do a hypothesis test and I find one of my gamma ij's, right, are significantly off 0, what does that mean? That means there is an interaction between factor I and factor j, right? That if I see something that comes from factor I and factor j, the mean is either higher or it's lower, right? That's what we're trying to say, okay? So what I'm asking you, is it possible that gamma ij is greater than or less than 0 significantly, right? Whereas both alpha I and beta I, alpha I and beta j are at 0. So this is what I'm asking you. Right, this is a specific question I'm asking. Is it possible that that's true? And what does that mean?
Sure, it's possible.
Okay, we have a vote for it's possible. What would it mean?
neither factor A or factor B individually have an effect, but when they're in some combination, they do.
So, yeah, exactly. Neither factor A nor factor B individually have an effect, but in combination they do. Can anyone think about an example of that? Right, where something individually does not have an effect, but if you put it together with something else, it does.
Grapefruits and heart medication.
I'm sorry?
Grapefruits and heart medication.
Grapefruit and heart medication. Do you want to expound on that?
Grapefruits inhibit an enzyme in your liver that's responsible for processing a bunch of drugs. So the FDA warns that you're not supposed to eat grapefruits.
So this is an example where, yeah, if you eat grapefruit and take a particular type of heart medication, that heart medication will not work. Okay? So this is kind of a negative example of that. There are other positive. What's a positive example of that? Anyone?
Those epoxy glues that you have to fix to make
Hmm.
them
Epoxy glues you gotta make, yeah, a lot of these glues, right? Factor A is, I forget one, there are two, there's like a base and I'm a horrible chemist. But there are two different things, right? If you mix them, the thing sticks. If you don't, right, it doesn't, right? Another thing is when people design drug cocktails, right? One individual drug may not work, but if you look at two, usually it's more than two together, but you have an effect, okay? So there actually are quite a few cases where before. Okay, so what are our statistics? So this is your test statistic for factor A. This is your test statistic for factor B, and this is your test statistic for factor AB. We had both of these before, right? We just added this new one. Okay? Okay, so yeah. I'll get back to this in a second. Okay. So what's sum square total? What is this explaining? What is this term explaining? This is a sum square error from what? What's x bar triple dot? It's just the mean of everything, right? And what are we looking at here? We're looking at every single unit. You subtract off the total mean, you square it, and you sum over what? All units. That's K. All, what's J? All levels of factor B, and all level of factor A, right? So this is my sum squared total. Okay, this is my sum squared A. So what am I doing? What's x bar triple dot again? It is just the total mean, right? What's xi double bar? What's x bar I double dot? That's the mean for what level? I in factor A. That's it, right? And so you're just asking, hey, what's a variation, right, over all of the levels of factor A? Okay, it's a variance. This is nothing but the variance over the levels in factor A, right? This is a total variance. This is the variance over the levels of factor A. Anyone want to take a guess what this is in English? This is a variance of over the levels of factor B, right? That's all this is. Oh my. Anyone want to take a guess what this is?
Mean of everything.
This is the mean of everything. What is this the mean of?
Factor
B.
or level J.
Level J. This is the mean of what?
Level I.
Level I. And what's x bar I j dot? This is the mean of what? This is the mean of what? This is the mean of the...
Interaction?
This is the interaction, right? This is like, look, let's look at everyone at the level ij, right? Everyone that's at the ith level in factor A and the jth level in factor B, okay? Let's look at all those individuals and look at what their mean is. Okay? So what is this explaining? This is a variation over what? This was a variation over what? All levels of
B.
B. This is a variation over what? All interactions, which means all joint levels of AB. Right? I look at AB together, and I'm looking at the variation over all groupings of AB. Okay?
See on that last slide, you find the some squared error by subtraction is that the total minus the other three.
Yeah. Okay, so these are these horrible formulas. Okay? This is what you do when you get a 2A in ANOVA. Okay? So this is for treatment A, this is treatment B, this is my interaction, this gives me the significance for treatment A, this gives me significance for treatment B, gives me the significance for interaction. Okay? Now let's talk about, if I wanted to do a 2A ANOVA, what do I need to tell the computer? Or a person, if you want to make a person do this, if you're sadistic. They used to make people do this back in the day. Right? You'd sign up and they'd send you to, the what's it, Rothenstad Agricultural Institute, and then you'd be there, working out all of these, on your days off when you're not spreading manure. I'm joking a little, but so what would you need to do? You'd give what? You'd give the computer what? You give them a set of people, right? And what would you have to specify for each person? Or each field? You give a bunch of units, and what would you have to specify for each unit? What?
Factor A, factor B.
Yeah, which factor they belong to. What level of factor A they belong to, and what level of factor B they belong to, right? And then everything else can be done from there on out. Okay. So here's a popcorn example. Okay, so what are our two factors?
Oil and air.
Nope, that's one factor. Right, so factor A is the type of popper. Is it an oil popper or an air popper? Okay, and then what's factor B? It's a brand of popcorn. Okay, we've got gourmet, national, and generic. Okay? And what are my measurements? What are my measurements?
Yield.
Huh?
Yield.
Yield. No. Actually, I guess you're right. Yeah, it is yield. I was going to say it's taste, but no, it's yield. You're right. I guess it says that. So just how much it puffs up, okay? So these are the row sums, these are the row sums, and these are the column sums, okay? Yeah.
What would be the levels?
Okay, so great. For factor A, how many levels do we have? 2, right? The 2 levels are whether it's oil-based versus air-based, okay? And then factor B, how many levels do we have?
3.
We have 3, okay? Okay, so then you can start computing things. This is a sum squared total. This is a sum squared A, this is a sum squared B, this is a sum squared AB, and given these numbers, we can compute the sum squared error. And then we can plug this into the ANOVA table. Okay? And you guys want to see what the result is?
Sure.
I'll tell you what, if you guys want to spend 5 minutes trying to work this out? No? Not really? Alright. How about this? We'll start next class by looking at these numbers, okay? So remember this and try to do it yourself. Okay? Yeah.
Are we going to have like plus and minus tables and stuff with all in our homework and lab?
What do you mean?
Just there's those big tables full of pluses and minuses. Just not for homework.
Oh, you mean in the lab?
Confounding.
In the what? I'm sorry?
In the homework
In
and
the lab.
Oh, you mean, are you gonna have that on the exam?
Are we going to learn it in class?
it's due on Thursday.
Oh, yeah.
Wait, learn what?
The fractional vectorial designs, the
Well,
plus and minus
actually-
tables.
I don't know.
Wait,
Yeah, for the-
actually, I'm not sure you are. Let me actually check, okay?
Oh.
What do we need that for?
The homework and the
Homework.
Analyze?
well, the lab, it just kind of tells you how to do it as
Oh.
is in the using MATLAB. But then MATLAB was wrong and the TA just gave it to us.
Wait, gave you what?
The fractional vectorial design.
The TA didn't give it to us. Wait, you
She just gave us the table of how to how to design your helicopters. Which helicopter gets what design and implementation.
oh, we just did what MATLAB gave us.
Yeah, that's what we meant to be doing, and then some reason some people were asking her like, okay, is this right? And she's like, no. Oh, wait, what? And she's like,
Oh, but it's MATLAB.
yeah, and then she,
Is this what you guys are talking about?
yeah.
Okay. So I guess I wasn't gonna teach you this, but just because I think you could have figured it out, but do you want to spend a few minutes going over it?
Yeah.
Okay. So what's going on here? What's run 1, 2, 3, 4, 5, 6, 7, or 8? So you had this in, what else did you have this in the homework and what else?
Lab.
And lab?
Lab 10?
So helicopters.
Oh, yeah, right there. I mean, the MATLAB program gives it to us. The frac, fac, gen.
Okay, so do you want to come, okay, what do you think the minuses and the plus means? Anyone?
Whether the factor is on or not.
So these are, okay, so if we go across here, right, what do we have? These are the effects, these are the code names, right? Punch, wing length, blah, 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 right? And then what do you think minus plus means? I'm sorry? They're just the levels, yeah. They're just assigning the levels. Okay? So, what does minus mean? 1, right? And then the plus here would mean 3. For the factor, for wing length, just minus means 3 inches, plus means 5 inches, right? And for a lot of them, they're just decimal. Okay, that's what the plus minus means, okay? But I guess that was not your confusion, right? What was, okay, so what was your confusion? sorry?
How do you know something's confounding?
What does confounding mean?
So what does confounding mean? So that's a good question. So okay, so first let's talk about what are the defining relations. So in run 1 we have minus A minus B minus C plus D plus E. What does that mean?
You're going to have to actually
Awesome.
Let me give you guys a bit of a hint. I should not have shown this. Okay, I'll give you this, okay? Don't tell anyone, okay? Don't tell me. Okay, so what are the defining relations? We have one ACD. Okay, what do we mean by ACD? Okay, if you look at A, can we tell anything apart? No, right? Because they're just assign them all the same, okay? From run 1, what can we tell apart? Huh? Right, so the question here is, in the way that the factors are set up, right? Can you tell apart A, B, D, E, right? Can you tell apart plus, plus, plus in A, B, D, E versus minus, minus, minus in A, B, D, E? Right? Can we tell apart all the ways you can get A, B, D, E, right? Versus how, let me rewrite. Okay, so let's say I have two factors, okay? And for each of these factors, I can get plus, minus, okay? To be able to identify or understand A, B together, what would I have to see? Right? What would I need to see in my run? How about we look at it this way? Let's say in run one, right? Let's say I saw, let's call this A, and let's call this B, right? Let's say in run 1 I saw plus, plus, right? In run 2 I saw minus, minus, minus. This is 2. And then run 3 I saw plus, minus, right? And then 4 I saw minus, plus. Okay? Yeah? Then can I tell, then is there a confound between A and B?
No.
Right? In this case, is there a confound between A and B?
No.
Why not?
They seem to be independent. Like, if you look for cause, there really isn't
I've
any.
given you all possible examples, right? I've given you all possible examples of A and B, right? So you should be able to fill out a table of A and B and tell me, you know, and assign probabilities for each of the elements, and we should be okay, right? So let's come back to this. So we're asking for, in this case, we're asking for defining relations, okay? So it's similar to what I was saying before, right? For which of these groupings, right, can I say, in the same way that I said something about AB. Okay? So that's what that first part of this question is asking. And then it starts asking about confounds, okay? And so basically you're getting a confound when you cannot resolve one of these. Okay?
So like, for example, when analyzing, we'd look at run 1 and compare that to run 3 and say, okay, we want to see if D causes E, like that. So we might think that it will from run 1, but looking at run 3, we can conclude.
So if you look at run 1, right, what happens? If I try to set C causes, well, if I said that C causes E, right, then what would I see? C, right, is minus here, you get a plus here, you get a minus here, and you get a minus here, right? So C probably does not cause E, right? So that's one thing you can resolve. So then you can start trying to go through and see what you can resolve.
Would there ever be any suppressing effects? Like a lack of something causes something?
So you shouldn't think this as minus plus, they're just two different groups, okay?
Okay.
So, question. So how can you say ABD when that's 4 letters but you only have 8 runs?
So you'll have to work that out, okay? It's your last homework. It's not that bad, but you can always come in and ask questions, okay? So actually, while I'm here, let me just give you the full numbers, and then we can. So I think we had this. Okay, so this is what we got for the popper. Okay? We had, this is the sum squared. This is our statistic, and this is the F value. This is what we get for the type of corn. This is what we get for the interaction effect. Okay? So we've got 0.3 for the interaction, 56.7 for the corn, 34 for the popper. So do you think these two are significant? The popper and the type of corn? Right? If you look at that, going back here, the popper and the type of corn. What about the interaction term? Probably not, right? Is this surprising to anyone? Did you expect there to be an interaction between the type of corn and the popper you use? Not really, right? So that's just that, okay?
Get back to the table real quick.
Yeah. So that's just what's going on here. Any questions about these numbers?
Yeah, what does the error tell
What does the error tell you? Good. What do you think the error tells you? Why do we put the error in there? So what we have here, right? I give you all of these errors and I give you the total error, right? The significance, we've explained, right? We want to say, you know, are one of these factors significant? Are the interactions significant, right? Why do we report the errors? Why do we care about the errors?
How much your significance
How much what?
how much your significance is.
How much your significance is? There's a reason why we have the errors. Remember, what are these called? These tests are called analysis of variance, right? Which means you're trying to do what to the variance? You're trying to analyze it. You're trying to partition the variances, right? So if you look at this type of error versus your total error, right? What is that explaining? This is how much error is left after we did what? This is how much error is left after we fixed the effect for the total mean, right? And then what other mean? The mean for the type of popper, right? The levels for the type of popper, as well as we fit what? The levels for the type of corn, as well as for the interaction, right? After we've modeled everything, which are, you know, total mean, factor A, factor B levels, as well as the interaction levels, this is telling me how much error is left over. Okay? This is just telling me how much error is left over, and then we, for example, we can compare that to the total error, right? So this is a total error we have. This is how much of it we have not explained, right? This remaining error is what? It's just noise in our model, okay? So that's why you might want to look at the error, okay? What's this 0.83 telling me? How much, this is the error, amount of error explained by what? The interaction term, and that's really, really small, okay? And then there's a lot of, most of my error is explained by the type of corn, right? And then a good amount of it is by the type of popper, right? So if you really want to ask which of these levels are explaining the most, right? What's explaining the most of the variation in yield? If you want to look at volume or yield, what variable, what factor is explaining it the most?
Corn.
It's a type of corn, right? Certain types of corn tend to pop, you know, I guess pop up fluffier than other types of corn. The machine makes a difference, but not as much as a corn. Okay? That's why you might want to look at the error. Okay? And tell you what, yeah, we don't need to start with this today. So we'll leave it at that. Okay? If you're still really bugged by that plus minus table on Thursday, we'll go over it one more time.